For today's lesson, we are going to cover sections 4.2 and 4.3 of our textbook, which pertain to relations. But before getting into the definition of what a relation is, I want us to build from our intuition based on our knowledge of a function. Because as we will see, all functions are relations. The converse is not true, so relations is more general. There are going to be relations that are not functions. So what is a function? If you open a calculus textbook, linear algebra textbook, you'll have the following definition. Let A and B be sets. A function f from A to B, denoted as f colon A arrow to B, is a mapping which takes each element A in A to exactly one output, f of A in B. We call A the domain of f. So in other words, a function is a mapping between two sets such that for every input there is exactly one output. But what if we wanted to describe how a function was as a set? And so that's the goal, the motivating question. We have this definition of mappings, but can we redefine a function as a set? Well, let's use our intuition from calculus. We know that if we have f of x is equal to x squared, so here we have a mapping going from the real numbers back to the real numbers. We have its graph. So we're looking now at the parabola. And we can go ahead, graph the parabola. And so when we graph the parabola here, we know that all the points on this have the form x comma x squared. So one candidate for the function as a set is its graph, which I'm going to denote by g. And so we can define g to be the set of ordered pairs x comma x squared, where now this here is in the Cartesian product of R with itself, so R2, and here, and that's it. We have our graph. And so that's all the points on the graph that we are used to. Now, this set G is actually how we are going to be defining a function. So for our course, G is the function that we used to call f. And so what we are going to do, notation-wise, is write the f, instead of defining it as a mapping, defining it as x comma x squared, and now here we have our element of R2, and so we have our definition here, or we could also write it as x comma y in R2, such that y is equal to x squared. And so both mean the same. But now, we are going to have the notation where f of x means the same as x f y. And so just keep this in mind notation-wise for now. F of x, x f y. And the key thing is that now we have that a function, in the way that we are defining it as a set, that this is going to be a subset of R2. So now if we were to abstract and go to arbitrary sets A and B, the way that we will be discussing the function is in terms of its set theoretic definition. So now it will be the ordered pairs A comma B in the Cartesian product of A and B, where B is equal to f of A. Of course, this is an abuse of notation because this is a circular definition because we're defining f in terms of its inputs here. But this is just to convey the difference between what we used to perceive as a function and how we are going to be defining it later on. And so in chapter 5, we will study functions. For now, I just want to motivate that we are redefining things that we are used to, but now as subsets of a Cartesian product of sets. One more example. Let's take a circle. So we have a circle. No, that looks more like an ellipse. So we have our circle here. And let's say that this is x squared plus y squared is equal to 1. So just a unit circle. Now, we could ask, is this a function? And we know that if we were to say, focus only, so if we were to be looking at inputs along the x-axis, it cannot be a function. Because if we chose, say, 0 as an input, it has two outputs, 1 and -1. And so this fails that aspect of it being, of having for every input exactly one output. But the circle is an example in this situation of a relation, because we could define the circle as the set of x comma y in the Cartesian product of the real numbers with itself, so R2, such that x squared plus y squared is equal to 1. And now this is a subset of R2. And so this is an example of a relation. So C is a relation. And so let's go ahead and now formally define what a relation is. And here it is. A and B are sets. A set R, which is a subset of the Cartesian product of A and B, is said to be a relation from A to B. But when we see this definition, we are not perceiving this geometric feature of it as we see with the case of the circle. Now that we have defined what a relation is, we can associate the words that we have been used to for functions to a relation. The concept of a domain, a range, an inverse. And so here's the formal definitions. So suppose R is a relation from A to B, then the domain of R is the set A and A, such that there is a B and B, so that the ordered pair is in the relation. The range has a similar definition, except now it's those B's and B's, so that there is some A and A, so that the ordered pair is in R. And finally, an inverse, where we have that our inverse is the relation from B to A, where now it's just the ordered pair, but flipped. Now it's B comma A in the Cartesian product of B and A, such that the ordered pair A comma B is in the relation R. We can also talk about compositions of relations. So if R is a relation from A to B, and S is a relation from B to C, we can talk about the composition. And so what I'm going to do is talk about this through a concrete example in just a moment. The first thing I want us to see is these three definitions in the context of functions that we have already seen previously. So to familiarize ourselves with this definition, let us consider f to be the relation x comma y in R2 such that y is equal to x squared. In other words, we are looking at our good old friend, the parabola, f of x is equal to x squared, but now as a relation. Similarly, we have g of g, which is now the relation x comma y in R2, y is equal to e to the x. Our good old friend, g of x equals e to the x. And when we investigate each of these definitions, we'll see that for both of these, it matches up with what we have come to expect. So we're looking now at the domain of f. And so what is the domain of f? Well, by definition, this is the collection of x in the real numbers. And then we have such that there is some y in the real numbers, such that a comma b is in f. X comma y is in f. But now to be x comma y in f, we know that that just means y is equal to x squared. So I'm going to go ahead and erase this. and we have y is equal to x squared. Well, we know that for every input x, we will have some y value corresponding to it. So we can plug in any real number x in here. So the domain here is just simply the real numbers. Similarly, if we had done the domain of G, we will get the same definition, since now it will be those x's in the reals, and then there exists a y in the reals, such that x comma y is in G. But now x comma y being in G is the same as y is equal to e to the x. That's what it means to be in G. And so we have y is equal to e to the x. Any real input is valid. So this here becomes just the real numbers. Now, what about the range? The range of f. By definition, this is those y in the reals such that there exists an x in the real numbers with y is equal to x squared. But now we are in trouble in terms of what can be the range. It's not going to be all the real numbers. And what I meant by trouble is that it won't just be as simple as just saying all the reals. Because as we know with the parabola, since we have x squared and x is a real number, x squared is always non-negative. And so what we end up getting here for all real numbers x, the outputs are always going to be non-negative, and so we have the non-negative real numbers, which I'm going to denote as r, and then subscript greater than or equal to 0 to denote the set of all real numbers greater than or equal to 0. And now we look at the range of G. And similarly, we're going to have those real numbers y, such that there exists some x in the reals, such that y is equal to e to the x. And in this case, we know that for every real input of e to the x, this is always going to be a positive quantity. And so now, this here will be, in the notation of calculus, the interval from 0 to infinity. Or in other words, those real numbers that are greater than 0. And so this one here, in notation from calculus, would have been 0 to infinity. Okay, so we have this. So we have now the domain and the range, and we see that this matches up with our previous understanding of domain and range. What about inverse? Well, we're now looking at f inverse. By definition, this is the set of all y comma x's in R2 such that y is equal to x squared. Now, this here becomes y comma x in R2, and if we solve for x, we get x is equal to the square root of y, or x is equal to the negative of the square root of y. And if we interpret this in the way we perceive functions, now we see that for every input, we actually have two outputs, except at most two outputs. Because if we were to plug in, say, 4 for y, we have two possibilities, 2 or negative 2. And so this f inverse is not a function. But as a relation, we can still talk about inverses. And so that is a benefit of this terminology, rather than functions, which is very rigid. In calculus, we did study inverse functions, but for things like e to the x, where we actually have an inverse. And so now, with what we have discussed, we see that G inverse, another way of writing this, is those y comma x's in R2, and this here is going to be x is equal to the natural log of y. And that would be the inverse function for G. And in this case, it will be a function. But as a relation, we don't have to worry about asking, is it a function? So next, let us verify that composition actually agrees with composition of functions as we have come to understand it. So suppose we wanted to do f compose g of x. Well, in the past we defined this to be f of g of x, and in the notation we have here with f of x being x squared, g of x being e to the x, this here would be f of e to the x, which in turn becomes e to the x, and then we square everything, and so exponent rules we have e to the 2x. And so that is the composition of f and g. Now, if we look at the set notation of f and g, if we did f compose g, then that will correspond to the existence of some b, and so in our case the reals, such that a comma b is in g, which is our r, and then b comma c is in s, which is our f. And so, in sum, we have the following. If we apply the definition, f compose g becomes x comma z in R2, there exists a y in R, and so that's there exists a b in b, such that x comma y is in g, and y comma z is in f. And the order matters. If we had done x comma y is in f, and y comma z is in g, we would have instead gotten g composed f. And so we have this here. So now, x comma y to be in g is to say that y is equal to e to the x. And similarly, to have y comma z is in f, and so here's our x comma y in R2 such that y is equal to x squared. So if y comma z is in f, that is telling us that z is equal to y squared. So we got this here. But now we are assuming the existence of a y, and we have y is equal to e to the x, and z is equal to y squared. So we can go ahead and substitute in this y into the other. And so now that we get x comma z is in R2, and now we have z is equal to y squared, which is e to the x quantity squared. And so we are back to what we had was f compose g. And so composition here agrees with our expected definition of composition that we are used to. So next, let us consider an example of relations that are not coming from functions we have studied previously. So let's define a, b, and c as given here. And so we have that the set R, as given here, is a collection of ordered pairs where the first entry is in A and the second entry is in B. And so in other words, this is a subset of the Cartesian product of A with B, and so it's a relation from A to B. Similarly, S is a subset of the Cartesian product of B and C, and so S is a relation from B to C. And we can view this in the context of functions and mappings if we do the following. So here's A. I'm going to put it here. So I've gone ahead, added our three sets A, B, and C. B is repeated twice, but we are going to go ahead and visualize our relations. So for the relation R, what we want to do is interpret the first ordered pair as the input, second ordered pair as the output. And so we have A comma E, and we're going to interpret that input A as going to output E, and so we have an arrow. Similarly, we have B comma F, and so we have an arrow going from B to F. And we have an arrow going from C to D. And lastly, we have an arrow going from C to E. And so we see that in this case, this would not be a function. because now C, the input C, has two outputs, namely D and E. But it is a relation, and we can visualize it in this way. Similarly, we can look at the relation S in the same manner. So we have the first entry in S is D comma G, and so we have an arrow going from D to G. We have one going from E to I, and we have one going from F to I. So next, let us consider S compose R. So if S compose R, this is going to be a relation, so it's a subset, but it's going to be a subset of, and the order matters, the first set in R, and the Cartesian product, so in that case, A, and then the second set in S appearing, so that will be C. And so this will be a subset of the Cartesian product of A with C. One way of perceiving this is that when we're doing the composition, we are going from A to B, and then we're going from B to C. And so if we look at the definition of composition, this is going to be composed of those ordered pairs A comma C in the Cartesian product of A with C, such that there is a B in B, such that AB is in R, and B comma C is in S. And so the main thing I want us to focus on is that the B occurring is the same. And so when we look at S and R, what we want to do is look at those ordered pairs. So here we have A comma E, and then we want to ask, where does E occur in S? And so we have E comma I. And so all of a sudden, we have A comma I. And now in the definition of the set, the direct is B in this situation is E, since we have that A comma E is in R, and E comma I is in S. And so A comma I, by definition, is now in the composition. Another way of perceiving that is that what we are looking at now is the following. So we are connecting the arrows just as before, and now what we get is that from E, so I'm just going to go ahead, connect E to E, and then we want to perceive the composition is that we're going from A to E, which is the same here, and then E is being mapped to I. Okay, let's do the next one. So for the next one, we're going to look at B comma F, and we want to ask, where does F occur in S? And so we see it only occurs here. And so now we have B comma I is in the relation S compose R. And we can use that intuitive notion again, where we have, so we have B mapping to F, and then F is being mapped to I. And so we got B comma I is on our composition. Let us continue. Now we look at the next one in the set. So now we have C comma D, and we see that D comma G is in here, so C comma G is in the relation of the composition. And lastly, we have C comma E, and that's going to be C comma I, since E and E is here. And so we got our relation for the composition of S with R. And so a way of perceiving S compose R, to keep in mind the order, because the order does matter, is that we're reading this from right to left. And so first we are thinking about the relation R as some mapping from A to B, and then we're going via S to C. And so that's essentially what we're having in a pictorial diagram. And so the main aspect for your intuition as we treat relations is that, yes, the definition is as a subset of a Cartesian product, but this is really the abstraction of mappings that we are used to. Of course, in this case, these are not necessarily functions. We have that one input may have more than one output. And we see that in the case of S compose R, we have C comma G and C comma I. So this here would not be a function, since the input C has two different outputs. But it still goes with our intuition of how we have thought about mappings in the past. And that's what we are doing with relations and later with functions. Just that because we want to put this all in the language of set theory, there is a trade-off in terms of these symbols that we are now having to introduce so we can view these relations as a set. So next we're going to look at Theorem 425, which gives us some properties of relations. Namely, if we have that R is a relation from A to B, so R is a subset of the Cartesian product of A and B, and similarly S is a relation from B to C, and T is a relation from C to D, then we have that the inverse of R, and then taking the inverse again, gives us back the same set. The domain of the inverse of R is the range of R, and similarly, range of R inverse is equal to the domain of R, and I'm just going to make a comment. R to the negative 1, so I'm going to call this here R inverse. I'm going to say it verbally. And then we have these compositions. The composition is associative. And finally, we have that if we compose S and R, then take the inverse, that it's the same as taking R inverse, and then, so first of all, in terms of the ordering, S inverse, then R inverse, in terms of the composition. Now, these two statements here, you'll recognize from calculus. When you first discuss inverse functions in algebra or calculus, one of the things that you show or look at is that the domains and range of the corresponding function and its inverse are the same. And so in the textbook, 1, 2, and 4 are proven. And so what I am going to do for our lesson is prove 5. And so let's go ahead and do that. So proof of 5. So the proof of 5, as is the case with 1, 2, 3, 4, is going to follow by a careful use of the definitions. So let's see that. So let's go ahead. So I'm going to observe that, and we're going to choose our C, A to be in the composition S compose R, quantity inverse. Now, the reason I'm choosing it this way is that by choosing C, A, now when we go through chase the definitions, A is going to be in A, C is going to be in capital C. And so it's just a choice so that the lowercase symbols match up with the capital symbols. And so by definition, this is equivalent to A, C being in R composed, S composed R. And so this here is by definition of inverse. All we do is flip the order of the ordered pair, and we are in the inverse of the composition. Okay, so the next step is to use a definition of what it means to be in a composition, and that means that there is some B. And so by definition there is AB in B such that A, B is in the relation R and B, C is in the relation S. And so this again is by definition of composition. So the next thing we are going to do is flip these around and apply the definition of the inverse of R and the inverse of S. And so now we have that B, A is in R inverse and C, B is in S inverse by definition. And now we are done, because what we want to show is that this is in the composition of R inverse, then S inverse. And so the order has been flipped. And so now we have C, B is in S inverse, and we have that common B over here in B, A in R inverse. And so now this here is equivalent to C, A being in the composition R inverse composed S inverse. And that finishes the proof. We are done. So now let us focus on the case when A is a set and R is a relation on A. So let A be a set, and R a relation on A. So that just means that R is just some subset of the Cartesian product of A with itself. And so R is an element of the power set of the Cartesian product of A with itself, which I'm going to abbreviate to just A2, or A squared. Now, what is an example? Well, we have many examples because we can now look at the power set. But one in particular is what we are going to call the identity relation. And the way that the identity relation is defined is that IA is the set of all ordered pairs A, A, where A is an A. And so we're just looking at all those ordered pairs of the form A, A. And so that's the identity relation. If we think about this as a mapping, this is just taking A back to itself, hence the name identity. So now let us move towards the real numbers. So let's go ahead and let A be the set of real numbers. We have already seen a number of relations on the real numbers in our previous work, and we have actually used them. So I'm going to define R and then subscript less than. And this is the relation where it's the collection of all ordered pairs A, B, such that A is less than B. We can also define greater, the collection of ordered pairs such that A is greater than B. And we can do that with equality, greater than or equal to, less than or equal to. And so all of a sudden, we now have a way of interpreting less than, greater than, and these other operations that we have seen in the real numbers as relations. And this warrants the following notation. So notation, if R is the relation from A to B, then we say, or then we write, A, R, B to mean A, B is in R. And so just keep this in mind, because this is a notation that is commonly used, A, R, B, and so A, B is in R. And the way to see how that notation matches up is that if we view from both of these, the less than and greater than, when we say that 5, 6, so 5 is less than 6, is in R less than, this by definition is the same as saying 5 is less than 6. And so what we are doing is going back, and I want to be careful here because technically if I erase a set and define it less than, then it becomes a circular definition because now the definition of less than is defined in terms of the inequality. And so I'm technically writing this as a set, but in practice we are viewing the relation less than as a relation. And so now when I write 5 is less than 6, we really mean R sub less than 6. So next we are going to consider an important definition that we are going to come back to throughout the course, and that is the following. So let us suppose that we have a relation R on a set A. So in other words, R is a subset of the Cartesian product of A with itself. Then we say that R is reflexive if for every single element X in the set A, it is the case that X are X. But now keep in mind, X or X is just a shorthand notation for saying the ordered pair X, X is in the relation R for every single A. And so we have that. Symmetric, so we say R is symmetric if for every single A in A, And for every single y in A, if we have that x comma y is in R, then so is y comma x. And finally, transitive. Now we have for every single x, y, and z in A, if it is the case that x are y and y are z hold, then we have that x are z. So let's see this through an example. So here are three relations on the real numbers, and we want to state whether they are reflexive, symmetric, or transitive. One of these we have already encountered, less than. We also now have greater than or equal to, and equality. And so we want to see, are each of these, which properties do these satisfy? Well, first off, let's look at the r less than. So we're going to be looking at this one here. Now, right off the bat, we know that this is not reflexive. Since given some real number a, so not reflexive, and so here's a counterexample. For a in the real numbers, it is not the case that a is less than a. That a is less than a, and thus a comma a is not in here. Or we can also use a notation r less than a, or a not less than b. And so we have these three notations which we can use interchangeably. So it's not reflexive. How about symmetric? Now the thing about symmetric is that we are assuming that it is the case that x are y. And so for symmetric, suppose, and so we have to assume that a comma b is in R less than, or equivalently, a is less than b. And then we want to show that b is less than a. But of course that is not true, since b is not less than a. We have that b comma a is not in here, and so this is not symmetric. What about transitive? Well, for transitive, now we have to assume that we have x are y and y are z. So suppose a is less than b and b is less than c. Then of course we know from our properties of inequalities that a is less than c. And so in this case this is true, so it is transitive. So this is transitive, but not symmetric nor reflexive. What about greater than or equal to? So this one I'm going to speak verbally since we have the same the ideas now. So for reflexive, in this case we do have it, because we do have that in this case a is greater than or equal to a. So it is reflexive. So for all real numbers a, we do have that a is greater than or equal to a, and so that holds. So we have reflexive. It is not symmetric though. Because we can have, say, 7 is greater than or equal to 5, but 5 is not greater than or equal to 7. Now, the main thing about this is that unlike the first example with less than, in that case, it is never the case it's symmetric. Now, with the greater than or equal to, in this example, we could have chosen 5. 5 is greater than or equal to 5, in which case it does satisfy that symmetric property. But for symmetric, we need this to be true for every single real number x and y, such that x is greater than or equal to y. And so we now have our counter example. So not symmetric, but greater than or equal to is transitive. And so you can verify that one. For equality, in this case, this here you can check it's reflexive. Of course, so here we have a is equal to a. So we will have it's reflexive. It will be symmetric. And it will be transitive. And whenever these three properties are satisfied, this is what is known as we call these types of relations equivalence relations. So I'm not going to discuss this further today, but that is a topic for our next lesson. And so equality is an example of an equivalence relation. So now let us prove some properties of reflexive, symmetric, and transitive that are equivalent to the given definitions. So here is our next result. So R is reflexive if and only if the identity relation I sub A is a subset of R. R is symmetric if and only if R is equal to R inverse. And R is transitive if and only if R compose R is a subset of R. And so in the book, 2 is proven, and so I'm going to focus on 1 and 3. So let's go ahead and get started. So for R is reflexive, so assume R is reflexive, then for each A in A, it is the case that A comma A is in R. So in particular, R is reflexive is equivalent to the identity relation IA, which we define to be A comma A is an A, is a subset of the relation R. And so we are done with 1. Okay, so let us go ahead and do 3. So for 3, let us go ahead and first assume that R is transitive. What we want to show is that R compose R is a subset of R, and since this is an if and only if, let me put in here the forward arrow to emphasize we're doing the forward direction. So we assume that R is transitive. Now what we want to do is show that R compose R is a subset of R. So let's go ahead and choose an element in the composition of R with itself. So now let x comma z be in the composition of R with itself. By definition, there is some y in the set A such that it is the case that x comma y is in R and y comma z is in R. And so here we just use the definition of what it means to be in the composition. And now we use the transitive property. Because for the transitive property, we have that if for every x, y, and z in A, if our x are y, so x comma y is in R, and y comma z is in R, then x comma z is in R. And so since R is transitive, we have that x comma z is in R, which shows that the composition of R with itself is in fact a subset of R. Let's do the converse. So for the converse, we are going to assume that R compose R is a subset of R. And so let us go ahead and choose some arbitrary x, y, and z. So let x, y, z be in A such that x comma y is in R and y comma z is in R. So notice, in doing so, I am taking some arbitrary choices x, y, and z so that the premise of transitivity is satisfied. And to show that it's transitive, we need to show that x are z. And the way we are going to do that is by our assumption that the composition of R with itself is a subset of R. So note that this is equivalent Note that by definition, we have that x comma z is in the relation R, compose R. And so we have this here. But now, as by the assumption, and since R compose R is a subset of R, we deduce that x comma z is in R, which now shows that R is transitive, and we're done. And so that finishes the proof. So let us consider a sort of a brain teaser to get familiar with the properties of the empty set and return back to our definitions of conditional and truth tables. So let us ask, what properties does the empty set have as a relation of A? We have seen that a relation is just a subset of the Cartesian product of A with itself, so naturally the empty set is always going to be a subset of the Cartesian product of A with itself. And so we could ask, is it reflexive? Is it transitive? Is it symmetric? And so let's see. So for reflexive, we need to be careful because the assumption is x is in A. So there are two possibilities. If A was empty, then this premise here would be false. We cannot have x is in A, and consequently, this here becomes a true statement. So if A is equal to the empty set, then the empty set is reflexive. There are no elements to choose from in X. And so now this becomes, we say, vacuously true. But what if A were non-empty? Then X, then IA is not going to be a subset. Let me write it like this. So the identity relation IA is non-empty, and this of course is not a subset of the empty set. So the empty set is not reflexive. But the empty set is symmetric and transitive, always. And the reason is by the definition. So if we look at the restated definition here, what symmetric means is that for every x and y, if xy is in R, then y comma x is in R. But the R in our case is empty. So this here is false. And we saw with the conditional, a false premise gives us a true statement. And so we have that the empty set is symmetric. And similarly, for transitive, we also have a conditional as part of our definition. And because R is empty, the premise here is false. And consequently, the conditional is true, making the empty set both transitive and symmetric. In the case of reflexive, the premise was x is in A, and so it does depend on whether A is empty or not. If A is empty, then we do get back that the empty set is reflexive. But if A is non-empty, then we have that A comma A being in R is false. And so now we have a true statement here is false here, so the conditional is false, and hence not reflexive. And so we're going to continue our discussion of relations in our next lesson, but we're going to be focusing on relations that satisfy all these properties: reflexive, symmetric, and transitive. And I'm going to also be posting a second video in addition to this one that's optional that will do 2 homework exercises from 4.3.